So now that we concluded who will go first, so I want to give the floor to Kurzböck from Virtual Vehicle, presenting the FlexCrash project, and especially a presentation titled FlexCrash, New Generation of Crash-Tolerant Crash Structures.
Exactly. Thank you
very much for being here.
Thank you for the opportunity to present our project, FlexCrash. So, as said here, we are working on the new generation of crash-tolerant structures. To give you a short overview of our project, we are actually in the middle of our project, so we have 4 years of project running time. We have about 10 partners from 5 different countries and about 4 million euros project budget. We are one of 3 projects funded in this cluster 5 call, testing safe lightweight vehicles. So the CINEA project is one of our sister projects, and also the project ROSI, which we are coordinating in Austria for the virtual vehicle. So I'm here for the FlexCrash project, so I also have some information if needed from CINEA and from the ROSI project. What does our consortium look like? We are, I think, quite a balanced project consortium from research centers, project coordinator EuroCAT. We have the FLAMINGo EVS and ourselves, the Virtual Vehicle Research Center. From the university side, we have the University of Munich and the IMC Krems in Austria. Industry side, GmbH technology, and also hooked up with Stellantis from Italy. And on the industry side, Geston and Aerobase from Sweden. And we have also included the standardized body, the UNE in Madrid, who is responsible for our legislative and patent work that we are doing in FlexCrash. So, what's the motivation and the ambition of FlexCrash project? The goal is to have a vehicle lightweighted as much as possible. The problem is the passenger safety on the other side, and also the sustainability of the used materials and the structures. So these 3 points do not fit well together. So when you're thinking of standard manufacturing processes, when you're going lightweighting in the vehicle body, you're losing passenger safety. You have to do that with active systems and other systems and so on. And you also have the problem with sustainability. So when you're thinking of lightweighting, when you go into fiber reinforced plastics, for example, then you have the problem with the sustainability on the other hand. So what's our way to deal with that? We want to try to focus on 5 pillars in our project. So we have 4 technological pillars and 1 legislative pillar in the project. The first pillar is our manufacturing and our manufacturing technologies. So we want to use 3 different manufacturing technologies, from extrusion technology, from high pressure die casting, and also from 3D printing, from additive manufacturing. So this looks like this. We have our base materials produced by extrusion or by high pressure die casting, and we are adding there some so-called AVFFs, so added value functional features with 3D printing, also called the LMD process from Fraunhofer. So with this technology, we can adapt our passive structure, our passive crash structure, to the needed purpose from the different load cases and crash scenarios, from actual loading scenarios and also from future crash scenarios, which will come a little bit later. So this is one of the pillars, of the technological pillars, is the manufacturing part. The second pillar is the design of such new crash-tolerant structures. We also mentioned in our proposal that we will use not only the passive side, of our crash structure, we want also try to include some kind of active system in our loading path, so to enhance or to be more precise for different load cases, especially in the future. Actually, we have these legislative regulations which a car manufacturer has to fulfill, and also this Euro NCAP regulations, let's say it that way, so these customer related requirements. And this can be done with this passive structure, as done normally in every car nowadays. But when it comes to these extended crash scenarios, for future crash scenarios, future crash situations with higher ADAS system, with better ADAS system, these crash scenarios will change in certain ways. We have wider crash angles, we have lower or less impact speeds in some scenarios, and to fulfill these, to protect the passengers and the occupants as much as possible, our target is to integrate the active system. Here the active system is designed with hydraulic actuators. We need therefore some sensor systems and so on. A little bit of problem, I cannot go in deep in this active system because we are actually working on a patent with Stellantis on this topic. So this active system will help us to prevent these future crash scenarios. The loading situation, or to reduce the loading situation on the passengers, on the occupants, and on the occupant car, for example. And the combination of these passive and an active system is for us one of the solutions to fulfill a wider growth of different crash scenarios in the future. In the end, it should be an optimal deceleration path, for example, for the passenger in the combination of these two systems. The third pillar is also coming from CINEA, as mentioned before. We are going to have an advanced testing and crash toughness and fracture and fatigue of these recycled aluminium, what we are going to use. So what we need for especially our work on the virtual side, on the validation of these material cards and these simulation methodologies we are using, we need a good and validated material properties. So we need to know what the material properties are, what the characterizations are, not only in the Young's modulus and fracture toughness. It also has to be these the braking behavior, the damage behavior, and also localizations of, especially with these high pressure die casting materials, we have some local effects that we have to visualize, and we have to validate in our material and simulation methodologies. And therefore, we are doing a lot of testing work on coupon level and also on component level to understand the material and to create and develop and validate it as material card for a good forecast probability. The fourth pillar is the crash simulation itself. So we have to show how we are going to deal with the production process, how we integrate that in our design phase, in our validation process, and in our crash simulations, and in our predictability of our methodologies. Therefore, we are going to use from the company Gestamp the GLab virtual model as a demonstrator. You can see here on the left side, this is this classical front end system with welded sheet metals, front bumper, these rail systems, these crash systems, and on the right side, the integration of the CINEA part. So we are going to use the CINEA parts as a baseline, extruded parts in the front crash system. And as some of you know, the CINEA part is not designed for crash purpose. So it is a quite heavy and stiff part. So the first step was to redesign a little bit the CINEA part. So this has to be done with topology optimization and crash simulation on the right-hand side. So we have to rethink a little bit or redesign a little bit the CINEA part for our crash purpose. So this was the first try. In the first step, we can reduce the weight. On the second step, we can optimize the crash bolts for the passengers. And this was the first tryout. And in this system, in this CINEA part on the right side, we are actually working on this active system to integrate in these CINEA parts and the active part to optimize further the weight and the crash pulse for the passengers. That brings me to the last pillar, this legislation pillar, the identification of the future safety needs. When these ADAS systems or autonomous driving cars are becoming more and more popular, the crash situation will change in certain ways. And for that, we have these mobility safety needs, these simulation methodologies where we can create crash scenarios with different boundary conditions. And for that, we have identified 3 different crucial crashes for the future. This is this on the right-hand side, nearly 90% crash, this 110-degree crash, and at least this 150-degree, which are the most crucial ones for our purpose and what we think in the future will be happening more and more. And these left turn across paths with opposite direction, you can see on that side is mirrored from this crash scenario here in the upper left corner. This is the most crucial one, and this is the one we are actually focused on for our validation of the crash system. So where are we actually now? We are, as said before, we are in month 25 actually, so halfway through the project. We have done our work on the crash information and improving crash simulation buildings, and we have this crash scenario generator where we can generate different scenarios, different loading scenarios for whatever we think of. And now actually we are working on the material and the manufacturing solutions, and parallel on the validation and the verification of our simulation methods. I think we are on a good way. We can show in different ways that we can lightweight the front-end system with different manufacturing technologies. We can integrate recycled aluminum in these components, and in the end we can validate all of these methodologies, technologies and so on to show how we can lightweight even more on different components all over the car, future body and weight. So thanks for your attention. Are there any questions?
Are there any questions from the audience? Yeah.
Thank you for the nice presentation. It was actually a multi-component presentation with a lot of different things in order to achieve, as far as I understood, one, the scope is to have this crash simulation results and to improve the life cycle of the vehicle, or
to improve the life cycle is what we want to achieve is that we can integrate these recycled aluminiums So not the life cycle at all. Life cycle will go better if we reduce the weight. So as discussed before in several presentations. So the goal is to integrate this recycled aluminium was developed in CINEA. And with the CINEA alloy, we are going to integrate different manufacturing technologies.
Okay, sorry, I was not aware about this collaboration with CINEA. I guess it's another project.
It's another project. It was mentioned before on this overview. Eurocup was also project coordinator of the CINEA, when I'm not wrong. But was also included in the CINEA consortium. And from there we get these parts and also the overview.
Okay, actually, this would have been my question more or less, starting with pillar 1, because I was not very clear about pillar 1, because I saw in the beginning you are using an additive manufacturing method in order to produce the components. So I was not clear about the materials used there. And my question would have been, if finally the use of certain materials that you are using, is it affecting, and to which percentage is it affecting this crash simulations? This would have been my question.
I don't think that we can say how many percent we are affecting the simulation. It affects the simulation because it is a little bit, it's comparable to classic prime aluminium. But the material properties differ a little bit, especially the scattering of the material. For example, my fracture, elongation and fracture, for example, is quite different to a prime aluminium. And for the crash simulation, this fracture and this damage is our main use. We use that for energy absorption. So we have to destroy components to absorb energy, and for that we have to clarify, or we have to test before a lot of different coupon level tests from the new used materials. This is the main point from the usage of the different materials. And the second point was before this manufacturing technology. So we are also trying to adapt to combine different manufacturing technologies together. So we are using these high pressure die casting, for example, and add on features with these additive manufacturing technology, and also on the extruded parts. So we try to be as thin as possible with the extruded part, for example, and add on with additive manufacturing, different patterns and so on, to be as stiff as possible in the end, but lighter than before.
Okay, clear enough, thank you. And one final question, and it came just in mind. Can you also integrate in your crash test calculations or whatever, because I'm not an expert to all of this, can you integrate parameters of recycling cycles? Or is it something?
Not directly.
No.
You typically use that for in LCA analysis or in these analysis of this for the crash simulation. We do not use that. So we get the different material properties, but we do not care about how these are. Yeah, exactly.
Okay, thank you.
One more question?
Okay. Thank you for the nice presentation. I think you mentioned at some point that so with the recycled material, of course, there's inherently some difference in the same elongation pattern. I guess perhaps more specifically for forwarding deformations when you form the material. Is this when you recycle, of course, there's going to be a difference in composition. Is this the reason why, or is there something inherently related to the recycling that leads to this difference in folding characteristics and deformation?
That's a good question, but I'm more the simulation guy. I'm sorry for that I cannot answer this question. Why is it that the recycled aluminium material is different to the prime aluminium? But what we can see here, just a few slides. We got this from Eurocat and our colleagues from Sweden. What we see here, for example, when we have this prime aluminium characterization and a little bit less, we have the secondary aluminium.
Okay.
And these difference we have to also include it in our simulation methodologies.
You account for it.
Yes.
Okay.
We have to deal with it in the topology optimization and also in the crash simulation.
Okay.
Because these influences our crash behavior a lot. And that's the main point, especially in the characterization. We took these data and go in our simulation models and try to be as good as possible, as thin as possible, and to
Okay. Thank you.
welcome.
Just if I could also make a question, picking up on the simulation, since you're an expert, as you said. Well, the question would be how these nice simulations that you showed would be validated with real crash tests.
So typically we are starting on coupon level. So we are simulating tensile tests, three-point bending tests, and so on. Then we are going on a component level. So we have, for example, the CINEA part, and we will crash only these parts. We have to validate on this level. And in the end, we are going to crash the full front end. So we are going to crash at least 3 full of these front end systems with just a passive crash system. The active crash system, we have to look on if it's possible to integrate it in the crash facility, because it's a little bit tricky, let's say it that way. But we are going up to the full front end. So what you can see in the direction on the right hand side. So these front end systems will be crashed at least 3 times at Stellantis test facilities, and not the full vehicle. So this full vehicle, what you see on the left top side, is only a virtual vehicle. It's not produced or manufactured, and we are just going for these subsystems.
But it will be a real crash test
Yes.
within the project.
Within the project.